Percents and ratios, introduction to percents. What is a percent? Well, fundamentally, a percent is a fraction. The word percent comes from the Latin per centum, which means per 100. Similarly, even the percent sign can be thought of as a stylized version of divided by 100. So that looks vaguely like that. Thus, percent means divided by 100, and 37% means the fraction 37 over 100, or the decimal 0.37. Similarly, 0.03% means the fraction 0.03 over 100, which of course is 3 over 10,000, or the decimal 0.0003. As you see, many of the rules covered in the decimal videos, especially multiples of 10, are relevant here. And if what we're doing here, moving the decimal place back and forth, if this is something that is not familiar to you, I highly recommend watch the multiples of 10 video before you watch the rest of this video, because the rest of this video is not going to make much sense if you don't understand how to multiply and divide by 100 and move the decimal place around. So, talking about that, changing from percents to decimals. This is simply dividing by 100, so we move the decimal point 2 places to the left. Here we have some percents. We want to change them to decimals. We move 2 places to the left. In some cases, we have to insert placeholding zeros. Changing from decimals to percents. Here we're doing the opposite, undividing by 100, which is essentially multiplying by 100. Thus, we move the decimal point 2 places to the right. We have several decimals here. We're going to move 2 places to the right. Notice that the final one, if we have a decimal greater than 1, it becomes a percent greater than 100%. Changing from percents to fractions. This is easy. We just have to put the percent over 100. After that, we may have to simplify a bit. So for example, 20%, that's 20 over 100, which is 1/5. 92%, that's 92 over 100, which is 23 over 25. 0.02%, which is 0.02 over 100, or 2 over 10,000, and that simplifies to 1 over 5,000. So all three of them very easily become fractions. Changing from fractions to percents, this is trickier unless you know the fraction to decimal conversion discussed in conversions, fractions, and decimals. So again, if you're not familiar with that particular video and those concepts are not familiar, please watch that and then come back and watch the rest of this video, because this video is not going to make a whole lot of sense if you don't know those conversions. Here we have some fractions. We want to change these to percents. In order to change them to percents, first we're going to change them to decimals. And we know that we can approximate 3/8 as 0.375. We can approximate 2/3 as 0.666 repeating. We'll write it here as 0.6667. Once we have them in decimal form, we just slide the decimal place 2 places over to get a percent. Of course, for fractions with 100 or 1,000 in the denominator, it's very easy to change to a decimal, which would give us a percent. So for example, 59 over 100, well, that obviously just becomes 59%. 17 over 1,000, that becomes 0.017, and we can write that as 1.7%. Those recommendations are for exact conversions from fractions to decimals. Often on the test, we need to approximate percents from fractions or from division. So for example, 8 over 33. Suppose we multiply the numerator and the denominator by 3, then we'd get 24 over 99. Well, 24 over 99 is going to be slightly larger than 24 over 100. Of course, when we make the denominator larger, we make the fraction a little bit smaller. 24 over 100, of course, is 24%, so 8 over 33 is going to be slightly larger than 24%. That's a very good approximation. 11 over 14. Here we can multiply the numerator and denominator by 7, and we'll get 77 over 98. And of course, that's going to be slightly larger than 77 over 100, which is 77%. So 11 over 14 is going to be something slightly larger than 77%. That's also an excellent approximation. So in summary, we talked about what a percent is. We talked about changing between percents and decimals, changing back and forth. We talked about changing back and forth between percents and fractions. And we talked about the very important topic of approximating fractions as percents. Working with percents. What is 55% of 400? Or 240 is 30% of what number? Now these could be test problems in and of themselves. They certainly would be things you might have to do in the context of a larger problem. So in this video I will show a few ways to tackle questions such as this. The first really big idea is percents as multipliers. The decimal form of a percent is called the multiplier for that percent. This is because we can simply multiply by this form to take a percent of the number. So when we're using percents as multipliers, here are the basic things to remember. Remember that is means equal. Remember that of means multiply. Change any percent to the multiplier form and replace unknowns with a variable. So for example, what is 80% of 200? The what, the unknown, that will be x, is, that becomes equal. 80%, that will become the multiplier, 0.8, and then we'll multiply that of times 200. So translating that sentence into math, we get 0.8 times 200, we multiply out, we get 160. Similarly, 240 is 30% of what number? 240 equals 0.3, 30% is 0.3 times, and then what number? X. So translating to math, and of course we divide, move the decimal place over, and divide out, we get 800. Now the second way to use this is in questions where we have to find the percent. So 56 is what percent of 800? So here we set things up again. 56 equals x times 800. We'll have to remember that that x, of course, is a multiplier. So we divide out, we can cancel the factor of 8, we get 7 over 100, which is 0.07. That's a multiplier which corresponds to 7%. Finally, percents and fractions. Use this approach only if the percent is a very easy fraction. For example, 1/2 or 1/4. So if it's a very easy fraction, then sometimes it's easier to change things to a fraction. So we get the question, what is 75% of 280? Well, it's much easier just to remember 75%, that's 3/4. What's 3/4 of 280? Cancel the 4's, we get 3 times 70, which is 210. Here are some practice problems. So pause the video and practice these now. Here are the answers. So in summary, use percents as multipliers, that is their decimal form, in the method for solving the simple percent problems. Using the same method to find an unknown percentage. So there, the unknown would be the percentage of itself. We'll get a decimal value. We'll have to remember that is the multiplier form, the decimal form of a percent. And then we can use certain fraction shortcuts for percents. Number sense is intuition for numbers and the patterns of arithmetic. It cannot be simply summarized and taught. It's a collection of pattern matching skills that you have to acquire over time. One usually gains number sense from playing with numbers and noticing patterns. Now I realize this might be very anti-intuitive to folks who don't like math that much. If you view math as a chore, why on earth would you play with it? But you really have to get curious about math and curious about the patterns to notice these patterns. Once you start noticing enough patterns, then you can start using them to your advantage. So I'm going to talk about one relatively simple pattern that you can use in this video. This method for handling percents involves using number sense. It takes a little bit of logic and creativity, but once you're used to it, it's considerably more efficient. Some folks will regard this approach as easy and obvious, while for other folks this may be a brand new way of thinking. And I'll just say, if what I'm showing in this video is completely obvious to you, don't even feel compelled to watch all the way through to the end of the video. Just skip to the summary and make sure you understand. Meanwhile, if what I'm showing here is brand new to you and you've never thought this way before, you might have to watch this video a few times to really get the hang of what I'm saying here. The beginning suggestion, start thinking about 10% of the whole and work from there. Sometimes it also helps to find 1% of the whole. So I'll work through some of the problems that appeared in the last video. What is 80% of 200? Well, one way to think about this, certainly 10% of 200 is clearly 20. We want 8 of those. 8 times 20 is 160, so that must be 80% of 200. 240 is 30% of what number? Well, here's how I'd think about it. If 30% is 240, we can divide this by 3 to get 10%. So 240 divided by 3 is 80, that's 10%. Well, clearly, if that's 1/10, then the whole thing should be 800. Notice that all of these are things we can do without a calculator. 56 is what percent of 800? Well, first of all, 10% of 800 is 80. We know 56 is less than that, so we know we're dealing with less than 10%. 1% of 800 is 8. We need 7 of this last piece. So 7 times 8 is 56, so that means we're dealing with 7% of 800. Again, everything here we can do without a calculator. 55% of 400. Here we're going to take a clever shortcut. Certainly we know 50% of 400, well that's 200. That's just half of 400. That has to be 200. Well, divide that by 10. 5% of 400 has to be 20. Well, now we can add those two. 50% plus 5% is 55%, and so 20 plus 200, that gives us 220, and that has to be 55% of 400. Here's another one, 37% of 700. You don't even need a calculator for this. Let's just think about this. 10%, that's 70, 1%, that's 7. I can do that in my head. Well, we need 3 of the first and 7 of the second. Well, 3 times 70, that's 210. I can do that in my head. 7 times 7, that's 49. I can do that in my head. Then we just have to add those. That's something I can do in my head. That's 259. So we can do this entire calculation without a calculator. Practice these. These are more practice problems. No calculator allowed. See if you can use the number sense method to figure out all of these. And you can pause the video to work on it. And here are the answers. In this video, we talked about a very efficient method of handling percents using number sense. The basic approach often involves finding 10% and sometimes 1% of the number. Percent increases and decreases. The test absolutely loves to ask about percent increase and decrease problems. This is perhaps one of their favorite kinds of problems. So here are a couple examples of things that you might see. We're going to be talking about this in the next couple videos. Remember what we said, first of all, about multipliers in the video working with percents. There we said that the decimal form of a percent was its multiplier. Here we will change that a little bit. The decimal form of p% is the multiplier for finding p% of something. So if I wanted, for example, 30% of something, I would use the multiplier, use the decimal form. If 0.30 is the multiplier to find 30% of something, but we will use different multipliers for a 30% increase or a 30% decrease, and that's what we'll be talking about in this particular video. First of all, let's talk about percent increases. So this may be phrased as y increased by 30% or x is 30% greater than y. Either way, this is a percent increase for y. Let's think about this. If y increases by 30%, the whole original part of y is still there, plus 30% more. Therefore, the multiplier for a 30% increase is 1 plus 0.3, which gives us 1.3. The 1 represents the whole that is there, that remains there, and then the 0.3 is the 30% that is added. And so it combines to our single multiplier, 1.3. In general, if the problem talks about a p% increase, the multiplier for a p% increase is 1 plus p% as a decimal. This is very, very powerful. Thus, the multiplier for a 46% increase is 1 plus 0.46, which is 1.46. So let's talk about how to use this in problems. An item originally cost $800. The price increased by 20%. What is the new price? So all we have to do is take 800 and multiply it by the multiplier for a 20% increase. 20% as a decimal is 0.2, so the multiplier would be 1.2. So this would be 800 times 1.2. And of course we can just multiply that out and get 960. Now I might do it this way with a multiplier, or I might do it just with some number sense. I know that 10% is 80, 20% is 160, so in other words we're adding 160, 800 plus 160 is 960. That's another perfectly good way to do this. After a 30% increase, the price of something is $78. What was the original price? That's a bit trickier. So it means we had some original x, we increased it by 30%, which would be a 1.3 multiplier, and that should equal 78. So x times 1.3 equals 78. We'll divide 78 by 1.3, slide the decimal place over, 780 divided by 13, that turns out to be 60, and that's the answer. Percent decreases. This might be phrased as y decreased by 30%, or x is 30% less than y. Either way, this is a percent decrease for y. Let's think about this. If y decreases by 30%, most of the original whole of y is still there, except for a 30% that's now missing. Okay, and one way to say it really is that if 30% leaves, 70% of it is still there. Therefore, the multiplier for a 30% decrease is 1 minus 0.3, which gives us 0.7. And this reiterates what I said a moment ago. If 30% leaves, 70% is still there. In general, if the problem talks about a p% decrease, the multiplier for a p% decrease is 1 minus p% as a decimal. So for example, if I want the multiplier for a 28% decrease, that would be 1 minus 0.28, which gives us 0.72. That is the multiplier for a 20% decrease. A $170 item is discounted 30%. What is the new price? So the multiplier way to do this, I form the multiplier doing 1 minus 0.3. I get 0.7. That's the multiplier for a 30% decrease. Then I multiply the price times that number, multiply out, and I get $119. Now, a totally different way to do it is, I might notice, again this is number sense, notice that 10% is $17, the 30% is 3 times that, $51. So in other words, 170 goes down by $51. And here's how I think about this. Price goes down by $50 and then it goes down by $1. Goes down by $50 from 170 to 120 and then by $1 from 120 to 119. That makes it very easy to do in my head. Here's another problem. After an item was discounted 80%, the new price is $150. What was the original price? You might want to take a moment just to work on this and then I'll show the solution. So here's how we'll solve it. It was discounted 80%, so the multiplier for that is 1 minus 0.8, which is 0.2. And so it means that the original x, which we don't know, is multiplied by 0.2 and winds up equaling 150. So we divide by 0.2, move the decimal, and we get 750. Now, a number sense way of approaching this, I might notice that if 80% is gone, 20% is left, that 20% is 150. Therefore, 10% is half of that, 75. Therefore, the whole is 750. That's kind of a number sense way of approaching it. Finally, finding the percent. Some problems give us the starting and ending values and ask us to find the percent of increase or decrease. Since the new equals the multiplier times the old, we could say that the multiplier equals the ratio of new price divided by old price. We have to remember that this ratio gives us a multiplier, and we have to change from that back to a percent. What was the price of an item increases from $60 to $102? What was the percent increase? So again, doing this a straight multiplier way, the multiplier equals new divided by old. So that equals 102 divided by 60. Divide both the numerator and denominator by 6. I get 17 over 10, which is 1.7. That's the multiplier for a 70% increase. For this same problem, I might notice that the difference is $42. And of course, 10% of 60 is 6, and there's 70 of those in 42. So that is another way to see that it's a 70% increase, 70% greater. The price of an item decreases from $250 to $200. What was the percent decrease? Well, again, we can use this ratio. Plug in 200 over 250, divide by 50, we get 20 over 25. We can also write this as 80 over 100. And of course, this is 0.8. That's the multiplier for a 20% decrease. I might also notice that the price drops $50, and $50 is 1/5 of 250. That's a drop of 1/5 or 20%. That's another way to see that it's a 20% decrease. If the price of an item increases from $200 to $800, what was the percent increase? Now, this is a really tricky one, and there's a trap here. Pause the video and think about this for a minute, and then we'll talk about this. So, obviously, the price was multiplied by 4. The trap answer is to believe that this is a 400% increase. That's a trap. Now, why is that a problem? 4 is the multiplier, so it's the multiplier for 4 minus 1, 3, or a 300% increase. Now, this is really subtle. We have to be careful here. 800 is 400% of 200. So that's one kind of question we can ask. 800 is what percent of 200? It is 400% of 200. But 800% is 300% greater than 200. Now that's a very different question. Not a question of what percent of, but what percent greater than. Those are two very different questions, and they have two different answers here. So in this video, we talked about percent increases and decreases. We talked about the multiplier for a p% increase, 1 plus p as a decimal. The multiplier for a p% decrease, 1 minus p as a decimal. And we talked about using multipliers to find the percent change. Sequential percent changes. So this is about when we have percent increases and decreases following each other, when you combine percent increases and percent decreases. There are a few common mistakes involving percent increases and decreases, and the test loves to exploit these common oversights. They love to write problems where people make very predictable mistakes. These mistakes center on scenarios in which 2 or more percent changes follow in a sequence. For example, you might have a certain percent increase in a price, and then an employee will buy it with a certain percent employee discount. And so you have a percent up, a percent down. How do they combine? So for example, Here's a typical problem. An item initially cost $100. At the beginning of the year, the price increased by 30%. After the increase, an employee purchased it with a 30% decrease, a 30% discount. What price did the employee pay? So pause the video right now, work on this on your own, and then restart the video when you're ready. The first thing I'll say is that the answer is not $100. That is the trap answer. That is the predictable mistake answer. More than half the people who take the test will guess that, and they will be wrong. That is the most common mistake in this whole subject. The same percent up and then down, or down and then up, does not put you back in the same place. People think, oh, a 30% up, 30% down, they cancel. They absolutely do not. You do not wind up back in the same place. We answer this using a product of multipliers. Though a 30% increase, that's a multiplier of 1.3. A 30% decrease is a multiplier of 0.7. And so we just multiply 100 by each one of those multipliers. So 100 times 1.3 times 0.7 gives us 91. And that's the actual price that the employee paid. Now this might be anti-intuitive for some people. Let's think about this. It starts out at 100. A 30% increase means it goes up to 130. Well, then the employee comes along with a 30% discount, but they're not getting a 30% discount on a price of 100. They're getting a 30% discount on a price of 130. And 30% of 130 is bigger than 30% of 100, which is why the amount it goes down is larger than the amount it goes up, which is why the employee winds up paying a price less than $100. Here's another problem. At the beginning of the year, the price of an item increased 30%. After the increase, an employee purchased it with a 40% discount. The price the employee paid was what percent below the original price? In other words, what percent below the price before the increase? So again, pause the video, take a moment to work this out on your own. The first thing I'll talk about here is the mistake. The common mistake, people are going to say, well, up 30%, then down 40%, 30 minus 40 is negative 10%, must be a 10% decrease. Guaranteed, more than half, maybe even 3/4 of the people who take the test will fall into this trap. It's as if the test writers just set up a huge butterfly net and people just run into it in hordes. It's absolutely 100% predictable how many people make this mistake. That's why it's so important to recognize this and understand not to make it. Whenever you have 2 or more percent changes in a row, never add or subtract the percents. That will always be wrong. You never want to add or subtract percent increases and decreases. Instead, what do? Of course, we use multipliers. We always use multipliers for percent increases and decreases. So a 30% increase, that's a 1.3 multiplier. A 40% decrease, that's a 0.6 multiplier. We're just going to multiply those two multipliers. They multiply to 0.78. 0.78 is the multiplier for a 22% decrease. And so this means that what we have going on here is a 22% decrease. The price that the employee paid was 22% less than the original price. Here's another. The price of a stock increased 20% in January, dropped 50% in February, and increased 40% in March. So in other words, that's the first quarter of the year. Find the percent change for this 3-month period, the percent change for the first quarter. So again, pause the video here and see if you can work this out. The first thing I'll say is that, of course, the mistake answer, the very predictable mistake that more than half the people who take the test will make, they're just going to do plus 30, minus 50, plus 40. That it gives us positive 10, so it must be a 10% increase. That's the mistake that people are going to make. Again, a very predictable mistake. The test writers absolutely love it when they can write a question that has such a predictable mistake. That's why it's so very important to understand the nature of this mistake so you don't fall into this trap. Of course, again, we're going to use multipliers. The multiplier for a 20% increase, 1.2. The multiplier for a 50% decline, that's 0.5. The multiplier for a 40% increase, 1.4. We're just going to multiply those three. To make things simple, I'm first going to multiply the last two. 0.5 or 1/2 times 1.4 will give me 0.7. And then 0.7 times 1.2 gives me 0.84. That is the multiplier for a 16% decrease. And so that's what's happened here. For the first quarter of the year, the stock decreased 16%. So in this topic, it's very important to understand both the nature of the mistakes, the very tempting mistakes, as well as to understand what the right thing is to do. Mistake number one, an increase and a decrease by the same percent do not get us back to the same original starting point. Mistake number two, in a series of percent changes, never add and subtract the individual percent. That will be wrong 100% of the time. Instead, what we're always going to do is figure out multipliers and multiply all the individual multipliers together. Simple and compound interest. This is one of my favorite topics here. Let's begin with simple interest. Well, simple interest is a mathematical fiction created to teach the idea of interest to grade school children. Absolutely no one in the real world uses simple interest. It is unlikely to appear on the test. With simple interest, the interest payment, the dollar amount of the interest payment, is exactly the same each time. So let's think about this. Bob deposits $1,000 in an account that yields 5% simple interest compounding annually. Well, 5% of $1,000 is $50. So what this really means is that every year Bob is going to get another $50 worth of interest. So in the first year, $1,000 plus 50, we get $1,050. Then in the second year, we add $50 again. Then we add $50 again. And in each year, all we're doing is we're adding that same amount, $50. And so the account is rising by $50 each year. The exact same amount, dollar amount, is added each time. Simple interest pays interest only on the principal and not on the interest. Thus, the amount of interest accrued makes no difference to the interest payment, which is the same in each period. And indeed, as this graph shows, if we were to graph the amount in the account versus time, it would rise as a straight line. All that's happening each year is another $50 is being added, so that's why it rises at a constant slope. Simple interest is not often tested directly, but, and this is very important, it can be used for estimation purposes. And we'll talk about this more later in this video. The big idea of compound interest is interest on interest. In compound interest, we get the percent of interest paid on the total amount that has already accrued in the account, principal plus all previous interest payments. Thus, the more interest that has accrued, the larger the amount of the next interest payment. No two successive interest payments are ever the same, so the dollar amount is always different. The entire amount experiences the same percentage increase in each period. So that's what stays the same. It's not the dollar amount that stays the same, it's the percent increase that stays the same. That's what's going on in compound interest. So for example, Bob deposits $1,000 in an account that yields 5% interest compounding annually. So that means that every year, the amount in the account is going to experience a 5% increase. So it's going to get multiplied by 1.05, which is the multiplier for a 5% increase. So we start at $1,000. So construct that multiplier, 1.05. Multiplied by 1.05, we get $1,050. Notice after 1 year, that we get exactly the same amount, either with simple or compound interest, and that will always be the case if we're compounding annually. That after 1 year, one compounding period, simple interest and compound interest get exactly the same amount. After that, they diverge. So after 2 years, we multiply 1050 by this same multiplier. We get 1102.50. Then multiply by that multiplier again and again. So these numbers are starting to get very hairy. So first of all, don't worry about getting these numbers by hand. You'd need a calculator to get these numbers. That's important thing number one. Important thing number two to notice is that, say after 4 years, simple interest would get up to $1,200. So here we have $1,215.50. We've done a little bit better than simple interest would do for us. Now, you might say, well, $15, what's the big deal about that? Well, think about it this way. Here we've only talked about 4 years. 4 years is a relatively short time in terms of investing, and we've only talked about a principal of $1,000. $1,000 is peanuts in terms of large-scale investing, and so you really have to think about this in terms of a more grand scale. With large amounts of money and or long periods of time, the difference between successive interest payments becomes substantial, and also the difference between the total amount gained with compound interest versus the total amount gained with simple interest becomes substantial. So big idea number one, compound interest always outperforms simple interest as long as there's more than 1 year. That is to say, as long as there's more than one compounding period. And this graph really summarizes it. The green line is the straight line of simple interest. The purple curve is the line of compound interest. Notice that it curves away from simple interest. It accelerates away from simple interest. So in the short term, it does a little bit better than simple interest, but then the longer we go, the more it diverges, and it does much, much better than simple interest does. By the end of this graph, notice that the compound interest total is over $1,000 more. That is the size of the principal. It's more than the size of the principal above the simple interest. Also notice, in Y years, the principal will be multiplied by the percent increase multiplier Y times. Let P be the principal and R be the multiplier. Then the total amount in the account after N years is P times the multiplier to the power of Y. We can even be a little more formal about this. Of course, if the annual percentage interest rate is I, then the multiplier for that, we change the interest to a decimal, that is divide by 100, and then add 1. That's how we get a percentage increase. So that's the multiplier for an I% increase. And of course, we're going to be multiplying by that Y times. Now here's what I'm going to say. I printed a formula here. Do not memorize this formula. That would be a big mistake. Instead, what I want you to do is understand the logic of how this formula was put together, and when you're doing a problem, rebuild the formula using that logic. Do not blindly memorize the result. So here's a formula, and I'll show what I mean. Sheila invests $4,000 in an account that yields 6% compounding annually for 8 years. What is the total amount after 8 years? So again, don't worry about getting the dollar amount. Just worry about getting the correct formula, the correct expression for the amount that would be in the account after 8 years. And I'll urge you to pause the video and try this on your own. So here's what I'll say. Here's how we'll approach this. The multiplier for a 6% increase, that's 1.06. It's going to get multiplied by that 8 times. So the total amount in the account is going to be 4,000 times that multiplier, 1.06 to the 8th. So that is the mathematical expression for the total amount in the account after 8 years. Now, of course, no one's going to expect you to calculate this without a calculator, but keep in mind that the test may not be asking for actual dollar amounts. The test may well list answer choices that are in this form. Certain amount times some decimal to some power, and then you have to recognize this particular one as the right answer. So sometimes the test actually does that, and just knowing how to construct the formula is enough to get the answer. Things get more interesting when we change the compounding period. Banks always give an annual percentage interest, but they may compound quarterly or monthly or even daily. For any compounding period smaller than a year, we need N, where N is the number of times that compounding period would occur in the year. So for example, quarterly, That means n equals 4. We're compounding 4 times a year. Monthly, n equals 12. We're compounding 12 times a year. Daily is 365. We're compounding 365 times a year. Technically, we'd be compounding 365 days during a regular year and 366 during a leap year. Let's not even worry about that. The test is not going to get into the region where you have to worry about leap years versus regular years. That's not something the test is going to do to you. Suppose the bank pays 5% annual interest compounding quarterly. The bank does not pay us 5% each quarter. That's not what's going on. That would be unrealistically generous. Instead, the bank pays us 5% divided by 4, which is 1.25%. That's the percent each quarter. In general, if there are n compounding periods in the year, we divide the annual percentage increase by n to get the percent for each individual compounding period. So we divide by 4 for quarterly compounding, we divide by 12 for monthly compounding. The correct multiplier now would be the multiplier for a percent increase of I divided by n. So writing this out very algebraically, 1 plus I over 100n, that's our multiplier. In y years, there would be n compounding periods each year, or n times y in y years. And so it means that we're multiplying by that multiplier ny times. So the total formula is this. And again, do not memorize this formula. That would be an exceptionally bad idea. Instead, I want you to think through the logic of it and, as it were, rebuild this formula each time using the logic of the situation. That is true understanding. Here's another problem. If Susan invests $1,000 in an account that yields 5% annual compounding quarterly, then how much does she have after 6 years? Again, don't worry about getting an exact dollar amount. Just see if you can build the correct formula. You can pause the video here and work on this. So the first thing I'll say is that 5% annual has to get divided by 4. So the quarterly percentage is 1.25%. The multiplier for that is 1.0125. So that's our multiplier. The amount in the account experiences that percent increase 4 times each year, or 24 times in 6 years. So we're multiplying by that multiplier 24 times. So the final amount will be the principal, $1,000, times that multiplier to the power of 24. Okay, so that's the expression. And again, if the problem is simply looking for building the correct formula, that's the correct formula. I'll also say that we could approximate this. Sometimes the test will want us to approximate. We can approximate using simple interest. So let's think about this. 5%, that's $50. So that means in 6 years, they'd get $50 6 times, $300. That means simple interest gives us $1,300. So we can estimate that the compounding interest over 6 years is going to be something slightly more than $1,300. Probably not going to be as large as $1,400. So that kind of gives us a ballpark range for how much interest we're going to accrue here. How does the size of the compounding period determine the interest earned over time? For this, we will need a large principal and a long amount of time. Let's say that the annual interest rate is 5%, the principal is $1 million, and the time is 20 years. So we're really pumping up both the amount that we're dealing with as well as the time to look at these subtle differences. So, on that scale, simple interest would give us $2 million after 20 years. Compounding annually would give us 2.6, and then we see the other numbers for compounding quarterly, monthly, daily, and hourly. Notice that as we up the compounding, the more and more compounding we do, the amount of total interest we get paid increases. As the compounding period decreases, the overall amount of interest earned increases. So that's a big idea also. You always do better with more compounding. In summary, we talked about simple interest, not very realistic, not likely to appear by itself, but an excellent approximation tool. We talked about compounding annually, then we talked about compounding other periods, quarterly and monthly. One big idea is that compound interest always pays more than simple interest. That's a really important idea. That's important especially when you're using the simple interest approximation. And also it's important to know that more compounding periods give us more money. Now we can begin ratios. Intro to ratios. What exactly is a ratio? A ratio is a fraction that may compare part to whole or part to part. For example, suppose in a class the ratio of boys to girls is 3 to 4. What does this mean? It means that the number of boys divided by the number of girls is a fraction that, in its simplest form, equals 3 over 4. This is one of the tricky things about ratios. The test will always give you ratios in their simplest form, and essentially always the absolute number of participants will be larger than the numbers in the ratio. So for example, ratio of boys to girls is 3 to 4 could possibly mean that we have 15 boys and 20 girls, or 21 boys and 28 girls, or 75 boys and 100 girls, or 300 boys and 400 girls, or 3,000 boys and 4,000 girls. In other words, we have no idea simply from the ratio what the absolute size of the group could be. The absolute size of the group could be anything. For some positive integer n, we definitely have 3n boys and 4n girls. We can definitely say that if we're given a 3 to 4 ratio. Here n is sometimes called the scale factor. Notice if we're given, once again, if we're given a ratio 3 to 4, we have no idea about the absolute size of either group. That's a big idea to which we will return. There are many different ways of presenting ratio information. The first, I'll call it P to Q form. The ratio of boys to girls is 3 to 4. We just spell it out literally like that. Second is fraction form. The ratio of boys to girls is 3/4. We can write it as a fraction. Third is colon form. This is very common on the test. The ratio of boys to girls. We read this as 3 to 4, but it's written with a colon. And then finally, a tricky one, I'll call this idiom form. For every 3 boys, there are 4 girls. So that's an idiomatic way in English to say exactly the same thing. All 4 of these contain exactly the same information. Now, of course, of these 4 forms, the most useful by far is fraction form, because when we rewrite the ratio in fraction form, then we can do math with it. Notice, in all of these, order is important. If we talked about the ratio of girls to boys, all the numbers would have to switch. So if we had girls to boys, that would be 4 to 3 or 4/3, something along those lines. To solve the majority of ratio problems on the test, we set 2 equivalent fractions equal. This is an equation of the form fraction equals fraction. An equation of this form is known as a proportion. And if you're not familiar with the mathematics of proportion, what you are allowed to do and what you're not allowed to do with proportions, I highly recommend watch the video Operations with Proportions. In particular, we often set the given ratio, the ratio given in the problem, equal to a fraction of the absolute quantities. So for example, here's a practice problem. In a class, the ratio of boys to girls is 5 to 8. If there are 40 girls, how many boys are there? So I'm going to suggest pause the video here and work this out on your own. I will say this is probably a simpler problem. Probably this is a little too simple by itself to be a test problem, but this skill could be part of a larger problem. This definitely could be a piece that you'd have to figure out as part of solving a larger test problem. So what I'll say is we solve by rewriting the ratios in fraction form and setting up equivalent fractions. So one fraction, of course, is 5 over 8. That's given. and that's a ratio of boys over girls, so I have to make another fraction of the form boys over girls. I have an expression, I have a number for the girls, 40, so I'm going to have to say that the number of boys is x, so that fraction would be x over 40, boys over girls. So x over 40, boys over girls, equals 5 over 8, boys over girls. Make sure that both fractions, the numerators and denominators, represent the same things. Well, in this particular proportion, I notice there's a multiple of 8 in both the denominators. So I can cancel that multiple of 8 with what we've called horizontal cancellation. Once I've done that, then I'm free to cross multiply. I get 8 equals 25, which tells me there are 25 boys in the class. Here's another one. In a class, the ratio of boys to girls is 3 to 7. If there are 32 more girls than boys, how many boys are there? So again, I'll recommend pause the video, see if you can work this out on your own, and then I'll show the solution. Now, some people may be tempted to use algebra to solve this. So, for example, one could assign variables. B is the number of boys, G is the number of girls. We could set up two equations. B over G equals 3 over 7. G minus B equals 32. We'd have two equations with two unknowns. We would be able to use algebraic techniques to solve this, but that would be very long and time-consuming. So I would not recommend that particular approach. Instead, I'm going to show something much simpler. I'll just point out ratio information often allows for a number of elegant shortcuts. Here, I'm going to say, let's rewrite the given information in terms of scale factor. The fact that we have a ratio of 3 to 7 means we could say the number of boys is 3n, the number of girls is 7n. We don't know what n is, but in other words, we can rewrite this in terms of n. Well, then it's very clear that the difference, 7n minus 3n, is 4n. 4n equals 32. Well, immediately we can solve for n and then solve for the number of boys. So that's a much more elegant solution. Scale factor is the magical link between ratio information and information about full quantities. This is a powerful shortcut about which to know. So far, we have talked only about ratios among the parts, but if we have a ratio term for each part, we can figure out ratios to the whole. For example, boys to girls is 3 to 5. Boys are what fraction of the whole? Well, one way to think about this is that boys are 3 parts of the class and girls are 5 parts of the class. So together there are 8 parts. Thus, boys constitute 3 parts of the total 8 parts, or 3/8. This is sometimes called portioning. Also, so far we have been talking about collections with only 2 sections, boys and girls. In fact, real collections of people and things may have 3, 4, or any number of categories. While hundreds of categories might be possible in the real world, the test will not make you deal with more than 3 or 4 categories. The test will always present ratios of this kind in colon form. For example, general purpose concrete is created using a 1 to 2 to 3 ratio of cement to sand to gravel. If we have 150 kilograms of sand available, how many kilograms of concrete can we make, assuming we have more than enough cement and gravel? So again, I'll say pause the video and see if you can solve this on your own. So the first thing I'll do to solve this is think about proportions. We want to relate sand, the part, to concrete, the whole. So there's 1 plus 2 plus 3 parts. That's 6 parts in the whole. So sand to the whole is 2 to 6. Sand to concrete is 2 to 6, and we can simplify that as 1 to 3. Sand accounts for 1/3 of the total weight of the concrete. So now we can set up a proportion. We have the fraction 1/3, and we can set that up to sand, which is 150 kilograms, over x, the number of kilograms of concrete that we don't know. We cross multiply, and we get 450. So we can make 450 kilograms of concrete given 150 kilograms of sand. In summary, we talked about ratios and a little bit about what they mean and what they don't mean. In particular, they don't mean anything about the absolute size, the absolute quantities. We talked about the scale factor, a very powerful shortcut. We talked about the various notations. Fraction notation, of course, allows us to do math with the ratios, which is very important. We talked about using scale factor notation to simplify calculations, especially involving sums and differences. We talked about ratios of parts to whole, the idea of portioning, and we talked about ratios with 3 or more terms. Combining ratios. Sometimes between different subgroups in a collection, a problem will give separately expressed ratios. So we'll have 2 or more ratios, and we'll have to relate these either to the whole or to absolute quantities. Before we begin, a few reminders. First of all, we typically write ratios as fractions, and one consequence of that is that we can write them as equivalent ratios, that is to say equivalent fractions. We know that 1/2 equals 5/10 or 10/20 or something like that, and so there might be times that we need to either simplify a ratio or to make it bigger in order to reconcile it with another ratio. Another trick is that we can use algebra. Suppose we have a ratio, say A to B equals 3 to 8. And that means that we can say that for some value of n, some unknown value of n, A equals 3n and B equals 8n. And therefore I can set up all kinds of algebraic equations, and then if I solve for n, I know the number of everything. As soon as I get the value of n, I know the number of everything. That's the advantage of using algebra with ratios. And finally, there's the very tricky issue of what we can and can't cancel in proportions. And so in a proportion, first of all, it's totally legal to cancel up and down. It's totally legal to cancel across 2 numerators or cancel across 2 denominators. Those are perfectly fine. Put happy faces there. But cross-canceling, that is always incorrect. Now, if this is news to you, if this is a new idea, please watch the lesson video, Operations with Proportions, in which I explain in detail which types of canceling you can do in a proportion and which types of canceling you can't do in a proportion. I'll assume you know all that in this video. The combining ratio scenario occurs when we are given 2 or more separate ratios within a larger group. Say in a group with type 1 and type 2, type 3 members, we might be given one ratio for type 1 to type 2 and a whole other ratio for type 2 to type 3. We have 2 basic strategies for approaching such questions. One strategy would be to find equivalent ratios. So for example, a ratio of 1 to 2 is equivalent to 7 to 14 or 13 to 26. And we'd adjust the equivalent ratios so that the common term, the one that corresponds to the same category in the 2 different ratios, is represented by the same number. So that's one strategy. Another strategy, if we have some absolute quantity, would be to either solve the ratio completely and use numbers, or to set up something algebraic and work with algebra. And so we have a few different approaches here that we're going to demonstrate in the few practice problems we have here. Here's practice problem number 1. Pause the video and see if you can solve this on your own. Okay. A certain high school team has only sophomores, juniors, and seniors. The ratio of sophomores to juniors is 2 to 3, and the ratio of juniors to seniors is 5 to 6. Sophomores are what fraction of the whole team? So here we have these 2 ratios, and the strategy we're going to use is to identify the common element, juniors. So juniors appear in both ratios, and so we're going to adjust the ratios so the number representing juniors is the same. So in the top ratio, juniors are represented by 3. In the bottom ratio, juniors are represented by 5. And so 3 and 5, the least common multiple is 15. We're going to get there by multiplying the top ratio, top and bottom, by 5, the bottom ratio, top and bottom, by 3. So those are our equivalent ratios. Now that juniors are represented by the same number in both ratios, we can combine the ratios. So now sophomores to juniors to seniors are 10 to 15 to 18. We can't simplify that. There's no single factor that is shared by all three of those numbers. No single factor bigger than 1. So we can't simplify that. But that is the overall ratio of sophomores to juniors to seniors. Well, now, if sophomores are 10 parts, juniors are 15 parts, and seniors are 18 parts, the whole is 43 parts. And so sophomores are 10/43 of the whole. Here's a second practice problem. Pause the video and then we'll talk about this. Okay, this problem is also a little bit on the easy side, perhaps a little bit easier than you'd see on the test, or one of the easiest possible things you'd see on the test. In a certain company, the ratio of programmers to marketers is 3 to 8, and the ratio of customer service reps to marketers is 2 to 3. There are 27 programmers. How many customer service reps? Well, here, of course, we could find equivalent ratios, but also we're given a number. So the strategy we're going to use, we can simply find the absolute quantity for each term one at a time. So we're given the number of programmers, and the only ratio with programmers is programmers to marketers. So we're going to have to use this to find the number of marketers. So 3 to 8 equals 27 to m. We're going to use the cancellation trick. We have a proportion. We're going to cancel across the numerators. Divide both numerators in that proportion by 3. Simplifies to a 1 and a 9. And now that we're down to 1, we can just cross multiply. So 1 times m equals 9 times 8, which is 72. So there are 72 marketers. Now that we know the number of marketers, we can figure out the number of customer service reps, because that ratio is 2 to 3. So we have 2 over 3 equals c over 72. Here we're going to divide both denominators by 3. So 24, so 72 divided by 3 is 24. We'll cross multiply here, and the number of customer service reps is 48, and that's the answer. Now here's a harder practice problem. This one takes a few more steps to tackle. Pause the video, and then we'll talk about this. Okay, 1 cup of butter is enough for 8 of Roger's cookies, and 1 cup of sugar is enough for 5 of Roger's cookies. He uses 15 more cups of sugar than of butter. How many cookies did he make? Well, we're going to have to do a few different things here. Here we're going to have to combine the ratios, combine the two approaches. First, finding a single ratio that includes all 3 elements, and once we have that single ratio, then using the parts to get algebraic expressions for the 3 elements. So part 1, combining the ratios. We know butter to cookies 1 to 8. We know sugar to cookies 1 to 5. The common term here are cookies, and so the least common multiple of 8 and 5 is 40. So we're going to multiply the top ratio by 5 over 5, multiply the bottom ratio by 8 over 8. Now we can put everything together in one big ratio. Butter to sugar to cookies, 5 to 8 to 40. Now with that combined ratio, use algebra. So there's our combined ratio, and we're going to say for some n, and n just represents kind of an abstract part. For some n, the number of cups of butter would be 5n, the number of cups of sugar would be 8n, and the number of cookies would be 40n. And so we get this directly from that combined ratio. All right, now we can use that last piece of information he used 15 more cups of sugar than of butter. That's a real word problem piece of information. So cups of sugar was 15 more than cups of butter, is what we're saying. Or in other words, cups of sugar is cups of butter plus 15. Or cups of sugar minus cups of butter equals 15. These are a few different ways to say the same thing. And this type of thinking, we're going to cover this type of thinking more in the word problem section, but this is just a preview of it. So we have 15 equals cups of sugar minus cups of butter. Well, we have algebraic expressions for these. Cups of sugar is 8n. We said that a few slides ago. Cups of butter is 5n. We have two algebraic expressions for these. Well, now we can just do algebra. With this equation we have, of course, 8n minus 5n is 3n. Divide by 3, we get n equals 5. Well, now we know the value of n, so now we can plug in and find all the absolute values. What we're looking for is the number of cookies. Number of cookies is 40n. Plug in 40 times 5, 200. We made 200 cookies. In summary, one method is to find equivalents so that common terms are equal in both ratios, then we can combine into one big ratio. Another method, if possible, solve for an individual value and use the ratios to solve for each additional individual values. And notice that in some problems we actually can solve in a few different ways, and in fact that's wonderful. You really understand a problem very well if you can take two entirely different approaches to it and get the right answer both times. That's always a good thing in your practice. Ratios and rates. Rates are ratios. Any ratio with different units in the numerator and denominator is called a rate. To solve most questions involving rates of all kinds, all we have to do is set up an equation of the form ratio equals ratio. We just match the units on each side. Remember that such an equation, fraction equals fraction or ratio equals ratio, is called a proportion. And if you're not familiar with it, it may be a good idea to go back and look at the video, Operations with Proportions, what you can do and can't do with a proportion mathematically. That video is in the fraction module. Rates are often expressed as so many units per units. So for example, all of these are rates. Many of these are drawn from science. The last two are special kinds, 60 minutes per hour or 360 degrees per revolution. These are examples of unit conversions. So these would be examples of things you would actually be expected to know. The other ones you would not be expected to know, but you would be expected to know that there's 60 minutes in an hour, and you can write this as a ratio. We would set this given rate equal to a fraction with the same units in the numerator and the denominator. So either the problem itself would give you one of the rates, for example, one of the blue rates, or you would know yourself something about the units and the way that the units are related. You set that up as a ratio, and then you set that equal to a fraction on the other side that matches the same units in the numerator and the denominator. Here's a practice problem. Pause the video, and then we'll talk about this problem. Okay, so this problem gives us a rate. It gives us the rate of 8 grams per hour. So that has grams in the numerator and hours in the denominator. So we're going to set this equal to a fraction on the other side that also has grams in the numerator and hours in the denominator. We're going to have 30 grams in the numerator, and then we're just going to have a variable. I'll call it h in the denominator. That's the unknown number of hours. The first step I'm going to do to simplify is I'm going to divide both sides by 2. So I'm going to divide the 8 by 2 and divide the 30 by 2. If that operation is an unfamiliar operation, if you're kind of shocked by that or didn't know that that was a possible thing to do with proportions, I highly recommend that you go back and watch the video, Operations with Proportions. Again, that video is in the fraction module. At this point, we'll cross multiply. Then to get the h by itself, we'll divide by 4. We get h equals 15 over 4 hours. Write this as a mixed numeral, 3 3/4 hours. we're asked when, which is actually a clock time. So we started at noon. 3 hours later would be 3 p.m. 3/4 of an hour is 45 minutes. So that means it's completely melted at 3:45 p.m. Here's another practice problem. Pause the video and we'll discuss this. A bumblebee's wing flaps 1,440 times in 8 seconds. So that's essentially a ratio. We could say it's 1,440 flaps per 8 seconds. How many times does it flap in a minute? Well, first of all, let's simplify that a little bit. 1,440 flaps in 8 seconds. I'm going to divide by 2. That gets me down to 720 over 4. Then I'm going to divide by 2 again. That gets me down to 360 over 2. And then I'm going to divide again. That's going to get me down to 180 over 1. So there are 180 flaps in 1 second. Well, we want the flaps in a minute. So clearly, what we're going to have to do is multiply by 60 seconds. Because there are 60 seconds in a minute. So the total number of flaps is going to be 180 times 60. We don't actually need a calculator for this. Let's think about this. Let's drop those zeros and make things a bit simpler. If we're doing 18 times 6, well, one way to think about this, the 18 is 10 plus 8. Well, I can do 6 times 10, that's 60. I can do 6 times 8, that's 48. I can add those two, that's 108. So now we're just going to add the two zeros. And so what we get is a product of 10,800. And that is the number of flaps in a minute. Here's another practice problem. Pause the video and then we'll talk about this. Okay, this is very tricky. We have a couple rates. We have the 20 grams per centimeter, we have the $50 per gram, and then we have this initial starting amount, the starting volume, which is 2 centimeters cubed. So first thing I'm going to do is I'm going to start there. I'm going to multiply those out, and I get 8 cubic centimeters. Well, I want to multiply that by a rate so those cubic centimeters cancel. So I'm going to multiply it by that first rate, 20 grams per cubic centimeter. That way the cubic centimeters will cancel. Then I'd be left with grams. Now I want to multiply something so the grams cancel. If I multiply now by 50 grams, $50 per gram, then the grams cancel, and I'll be left with units of dollar. And that's what we're looking for. We're looking for the price. So I'll point out here, this is actually very easy now because 20 times 50 is just 1,000, times 8 is 8,000. So that would be worth $8,000. In summary, when you see problems with rates, remember you can set up proportions. Always remember to make sure that the units of the numerator and denominators match.